Welcome to the Deep Dive, where we plunge into complex topics to extract the most potent insights, giving you that aha moment without, all the information overload. Today, we're diving headfirst into the molecular architecture of organic chemistry, specifically the fascinating world of conjugated alkenes, and one of chemistry's most powerful tools, the Diels-Alder reaction. Our mission for you today is really to pull out the fundamental principles, the unique ways these molecules react, their precise mechanisms, and the crucial problem-solving tips. We're using organic chemistry, offered Dummies, seconded, as our guide. We're going to try and demystify how something as simple as, electron distribution can completely alter a molecule's behavior, and also how a Nobel Prize-winning reaction lets chemists build incredibly intricate structures, like things for new solar cells or pharmaceuticals, with surprising precision.
And that's exactly what makes this deep dive so valuable. Understanding these concepts, conjugated systems, and the elegant simplicity of the Diels-Alder, it isn't just about passing an exam, it's really about grasping the core logic of organic reactivity. And critically, how chemists design and, build the complex molecules that shape our world. It's truly foundational stuff.
Okay, so let's start right at the beginning then. We know alkenes have double bonds, but what's the fundamental difference between a double bond that's considered conjugated and one that's isolated? How does that distinction, change everything?
Right. It really comes down to spacing. Simple as that almost. In a conjugated alkene, you've got two or more double bonds separated by just one single carbon-carbon bond. So think of a pattern. Double, single, double. A classic example everyone uses is butadiene. Two double bonds, one single bond right in between. Isolated double bonds, though, they're separated by more than one single bond. So you got a longer chain of single bonds breaking up that single-double sequence. And the key takeaway here, and it's the big one, is that conjugated alkenes are significantly more stable than their isolated counterparts. Much more stable.
More stable. Why is that? What makes them so much more stable?
Yeah, it's because of something called resonance. In a conjugated system, like our butadiene example, the electrons in those double bonds, they aren't just stuck between two carbons. They can delocalize, spread out, basically across the entire conjugated part of the molecule. This delocalization, this spreading out, it disperses the electron density. And if any charge forms, like in a reaction intermediate, that charge gets spread out too. That makes the whole thing inherently more stable. Isolated double bonds just don't have that extended network. Their electrons are pretty much stuck in that one double bond. It's kind of like, think of a crowd in a room. If everyone can spread out into adjacent rooms connected by doors, it's more comfortable, right? Less congested. Same idea for electrons here.
Right, okay. I can really visualize that spreading out now. Makes sense. So that increased stability, the electron delocalization, that must have some pretty big implications for how these molecules react, right? Like when we think about adding hydrohalic acids, HBr or HCl, something you've seen with regular alkenes, you're saying conjugated alkenes behave differently.
Yes.
How does that actually play out?
That's exactly right. Their reactivity is quite distinct because of that resonance. So if we walk through the mechanism, the first step is still what you'd expect. One of the double bonds gets protonated by the acid, you form a carbocation, and usually, the proton adds in a way to make the most stable carbocation possible, typically secondary or tertiary, not primary if possible. But here's the kicker. Because of the conjugation, this carbocation that forms isn't just one structure. It has two major resonance structures. The positive charge isn't stuck on just one carbon. It's effectively shared or delocalized between two different carbons in the system. Usually carbon 2 and carbon 4, if we number the chain starting where the proton added to carbon 1.
Two resonance structures. So the positive charge is kind of in two places at once, or shared.
Exactly. The true structure is a hybrid, a blend of those two resonance forms. So both carbon 2 and carbon 4 have some partial positive character. And because of that, the halide ion, like bromide from HBr, when it comes in for the second step, it has options. It sees positive charge building up on both C2 and C4. So it can attack carbon 2, the one right next door to where the proton added. That gives you what we call the 1Br2 addition product, hydrogen on 1, halide on 2, or it can attack carbon 4, the one further down the chain where the charge resonated to. That gives the 1There4 addition product, hydrogen on 1, halide on 4. So from the same starting materials, you can get two different constitutional isomers.
Whoa, okay. Two different products from the same starting point. That's interesting. And potentially messy if you only want one. So how do you control which one you get more of? You mentioned earlier this is where temperature comes in. How does changing the heat actually steer the reaction to make more 1There2 versus 1There4? That seems super important for synthesis.
It absolutely is a critical point, and it's a beautiful illustration of a really fundamental concept in organic chemistry. kinetic versus thermodynamic control. You see, the ratio, the amount you get of the 12-2 product versus the 1-4 product, it's highly dependent on the reaction temperature. For example, if you run the reaction at lower temperatures, say around 0 degrees Celsius, maybe even colder, you predominantly form the 12-2 addition product. That's the major one. But if you crank up the heat, maybe run it at 40 degrees Celsius or higher, the tables turn. Now the 1-4 addition product becomes the major player.
Okay. Low temp gives 1-2, high temp gives 1-4. Why? What's happening at the molecular level with the energy?
Right. So to understand why, let's picture an energy diagram, like a landscape with hills and valleys. Both reaction pathways, the one leading to the 12-2 product and the one to the 1-4, they start from the exact same place. That initial carbocation intermediate we talk about, the one with the resonance, but then the paths diverge. To get to the 12-2 addition product, the energy hill you have to climb in that second step. The activation energy is actually lower. It's an easier climb, so that reaction step is faster. The 12-2 product forms more quickly. However, and this is key, the 12-2 product itself is generally higher in energy. It's less stable than the 1-4-12 product. Now, at low temperatures, there isn't a lot of extra energy floating around. So once that 12-2 product forms, even though it's less stable, it doesn't really have enough energy to easily revert back to the intermediate or change into something else. It's kind of stuck. So because it forms faster and gets trapped at low temp, it dominates. We call this the kinetic product, the one that forms fastest.
Okay, kinetic means faster formation, lower energy hill to climb, favored at low temps because it gets trapped. Got it. What about the 1-4 then?
So the 1-4 addition pathway, that second step, has a higher energy hill to climb. Its activation energy is greater, meaning it forms more slowly than the 12-2 product. But, and here's the payoff, it leads to a product that is more stable. It sits in a deeper energy valley. It's the lower energy product overall, usually because the double bond ends up more substituted, which is generally more stable. Now, at higher temperatures, there's enough energy for everything to be reversible. Molecules are banging around more, reactions can go forwards and backwards, products can potentially go back to the intermediate. When a reaction can reach equilibrium like this, it will always, always favor the formation of the most stable, lowest energy product possible. The system settles into its most comfortable state. So at high temperatures, even though the 1-4 forms slower initially because it's more stable and the reactions are reversible, it eventually accumulates and becomes the major product. We call this the thermodynamic product, the most stable one.
Yeah, okay. So thermodynamics is about overall stability, the final energy state. Kinetics is just about the speed of getting there.
Exactly. Kinetics is about rates, driven by activation energies, those energy hills, favored at low temp, irreversible conditions. Thermodynamics is about stability, driven by the overall energy difference between start and finish, favored at higher temp, reversible equilibrium conditions.
And the practical rule then is super clear.
Yeah, pretty straightforward. Want the 12-2 product. Run it cold. Want the 1-4 product. Run it warmer. Give it time to reach equilibrium.
That's really powerful. Just by adjusting the thermostat, basically you can dictate which isomer you make. Incredible. Okay, so that's how conjugation affects addition reactions. But what if we use this conjugation for something? Well, even more constructive, like building rings. This brings us to the Diels-Alder reaction. I've heard called, kind of funky, but also one of the absolute most valuable reactions in organic chemistry. Nobel Prize winning, even. What makes it so special? So indispensable for making new molecules.
Oh, it truly is a synthetic powerhouse. It's one of the cornerstones for building complex cyclic and bicyclic structures. Absolutely fundamental. The basic idea is that you take a conjugated diane, that's our double single double unit, and you react it with an alkene. But in this context, we give the alkene a special name. A dienophile literally means diane lover.
Yeah.
And the magic happens when these two, the diene and the dienophile, undergo what's called a cycloaddition. They react together to form a brand new six-membered ring.
A six-membered ring.
Yep.
It's like that. What's the mechanism? Is it complicated?
That's the beautiful part. The mechanism is incredibly elegant because it's a single-step reaction. It's what we call a concerted process. There are no carbocation intermediates, no anions, none of that stuff forming along the way. All the bonds are made and broken essentially simultaneously in one smooth, synchronized dance of electrons. You start with 3 double bonds, 1 in the dienophile, and in this one step, those electrons rearrange to form 2 new carbon single bonds that stitch the molecules together, and 1 new carbon double bond within the newly formed 6-membered ring. It's remarkably efficient. You increase molecular complexity significantly in just one step.
Well, one step, multiple bonds change. That's efficient. Does it work with any dialin and any alkene? Or are there preferences?
Good question. There are definitely preferences that make the reaction work much better, much faster. For the diene, the reaction tends to go faster if it has electron-donating groups attached. Think of groups that can push electron density into that conjugated system, like ether groups, OR, alcohol groups, OH, or even amine groups, NR2. They make the diene more electron-rich. And conversely, for the dienophile, the diene lover, it reacts fastest when it has electron-withdrawing groups attached. These are groups that pull electron density away from the dienophile's double bond, things like cyano groups, CN, nitro groups, NO2, or carbonyl compounds, esters, aldehydes, ketones, acids. This electron push-pull between the diene and dienophile helps lower the activation energy, making the reaction zip along. And there's another really critical requirement for the diene. It must be able to adopt what is called the cis conformation.
Cis, what does that mean?
It means that the two double bonds in the diene need to be oriented on the same side of the single bond that connects them. Imagine the diene shaped like a C. If the diene is stuck in the S-trans conformation, where the double bonds are on opposite sides, like a Z or stretched out, the reaction just won't happen. The ends of the diene, carbons 1 and 4, are too far apart to both connect with the dienophile at the same time. This is why dienes that are already part of a ring, like cyclopentadiene, react incredibly quickly in Diels-Alder reactions. They are locked in that required cis shape, perfectly pre-organized for the reaction, no rotation needed.
Okay, so electron-rich diene, electron-poor dienophile, and the diene needs to be in that C shape, the C size. Got it. What about stereochemistry? Does it just make a random mix of isomers, or is it precise?
That's another superpower of the Diels-Alder. It's highly stereoselective, meaning it preferentially forms one specific stereoisomer, and it exhibits retention of configuration from the dienophile. So if you start with substituents on your dienophile that are cis on the same side to each other, they will remain cis in the six-membered ring product. If they start trans on opposite sides, they stay trans in the product. The reaction perfectly preserves that starting geometry. It has memory.
That's incredibly useful for control.
It is, and it gets even more interesting when the diene itself is cyclic, like that cyclopentadiene example.
Right.
When that reacts, you don't just form a simple six-membered ring, you form a bicyclic product, a structure with two fused rings, kind of looks like a basket or a boat with a bridge.
Bicyclic. Okay. Does the stereochemistry get more complicated there?
A little bit, but there's a strong preference. You generally get two main possibilities for how the dienophile substituents add relative to that bridge: endo addition and exo addition. The endo product is the one where the substituents from the dienophile are pointing sort of down or under the main bridge of the bicyclic system. Think of them tucked away. The exo product has them pointing up or out, away from that bridge. And the Diels-Alder reaction, for reasons involving secondary orbital interactions we probably don't need to get deep into now, almost always shows a strong preference for forming the endo product. That's usually the major isomer you'll isolate.
Endo preferred. Okay. So the precision is just built right in, isn't it? Specific conformations needed, specific electronic preferences, preserves stereochemistry, even prefers endo for bicyclic products. That's amazing. Right, let's get practical then. Say you're faced with a Diels-Alder problem. You've got a dienophile, maybe they have some groups attached. How do you actually predict the product? What's the mental roadmap, the step-by-step checklist you run through?
Great question. Because, yeah, looking at them initially, they can seem confusing with all the arrows people draw. But there's a pretty reliable four-step mental checklist that makes predicting the products much, much simpler.
Okay, walk us through it.
All right. Step 1. Orient your diene and dienophile correctly. Mentally, or on paper, arrange them so the diene's double bonds are pointing toward the dienophile's double bond. And critically, make sure that diene is in the cis conformation. If it's drawn S-trans, you'll need to imagine rotating it around that central single bond until it looks like that C shape ready to react, like a pair of pincers ready to grab the dienophile.
Okay, line them up, make sure the diene is C-shaped. Step 1.
Step 2. Number the carbons of the diene from 1 through 4. This isn't for formal naming, it's just a bookkeeping tool. Pick one end as carbon 1, the other end of the conjugated system is carbon 4. This helps you track exactly where the new bonds form.
Number 1 to 4. Got it.
Step 3. Work the reaction. This is where you actually draw the new bonds and adjust the old ones. Think about the electron flow. You form a new single bond from carbon 1 of the diene to one side of the dienophile's double bond. You form another new single bond from carbon 4 of the diene to the other side of the dienophile's double bond. At the same time, you erase the double bonds that were between C1, C2, and C3, C4 in the starting diene, and you draw a new double bond between carbons 2 and 3 of the original diene carbons. That's your six-membered ring formed. And just a detail, If your starting diene was cyclic, those other carbons that weren't part of the 1 to 4 system, they often kind of flip up and form that characteristic bridge over the new ring, making it bicyclic.
Okay, connect 1 and 4 to the dienophile, move the double bond to between 2 and 3. Makes sense. Final step.
Step 4, and this is crucial. Check the stereochemistry. Remember our rules. If there were substituents on the dienophile, were they cis or trans to start? They must stay that way in the product ring. Preserve that geometry. And if you formed a bicyclic product, double check that you've drawn the endostereoisomer as a major product. That means any substituents from the dienophile should be pointing sort of down under that bridge you formed, not sticking up toward it. Follow those 4 steps. Orient, number, work the reaction, check stereochemistry, and you can systematically figure out the product of pretty much any standard Diels-Alder reaction. It takes practice, but it breaks it down nicely.
That is an incredibly clear roadmap. Orient, number, react, check stereo. Really helpful. It shows how you can take something that looks complex and just, make it approachable with the system. This whole deep dive has been fantastic. It really highlights the utility and elegance of these conjugated systems, and especially the Diels-Alder. It's fascinating how understanding these concepts like kinetics versus thermodynamics directly impacts what you actually make in the lab. It gives chemists real control.
Absolutely. That ability to predict and, more importantly, control the outcome of reactions, particularly sophisticated ones like the Diels-Alder, that's what empowers chemists. It lets us build molecules with increasing complexity and function. And this isn't just, theoretical. It's how new drugs are designed and synthesized, how advanced materials with specific properties are created, how components for, say, better solar cells or catalysts are developed. This chapter, this area of chemistry, really shows how a few fundamental principles about electrons and energy can become incredibly powerful tools for innovation.
Couldn't agree more. It's really inspiring stuff when you break it down. What an insightful journey into the heart of organic chemistry. Thank you so much for joining us on this deep dive into conjugated alkenes and the Diels-Alder reaction. We hope you feel a little more well-informed, maybe a little more curious about how molecules dance, and perhaps even inspired by the sheer precision and ingenuity involved. Until next time, keep exploring the fascinating molecular world around you.